Hey kiddos, today we're going to talk a little bit about Gibbs Free Energy. Now why Gibbs Free Energy matters to us so much is a little bit of what we're going to talk about, but essentially Gibbs Free Energy tells us, is this reaction going to happen? Like, is this a favorable reaction to happen? We would use the terminology, is it thermodynamically favorable? Is it spontaneous, we might say. And so to know that is really important to us in chemistry, because this is going to be, hey, do I have the energy to make this next reaction happen? If we're talking about large biochemical cycles and chains of reactions, many of them are not favorable, and so I need something that is favorable to drive them. And so Gibbs Free Energy comes a lot into play in biology. Of course, in chemistry, it's essentially one of the driving forces behind all of our reactions for us. It helps us to determine whether or not reactions are really going to occur. So this is the equation for Gibbs Free Energy, and we're going to break this apart and talk about each term and throw some other terms in the video as well. Delta G itself is Gibbs Free Energy, and when we get to the end of this, I'll talk specifically about why it's free energy. Delta H is a term called enthalpy. Now enthalpy is similar to something that you probably learned in Chem 1 class, which is Q. If you remember correctly, Q is heat, and we measure that in joules or maybe in calories, or kilojoules and kilocalories. And enthalpy is sort of a specific case of Q. For pretty much any of the purposes that you'll be doing until maybe you get up into your higher level college classes, you can essentially treat enthalpy and heat the same way. What the difference technically is that enthalpy is heat if a process is carried out at a constant pressure. And of course, for us, most of the time for organic chemists, and really for a lot of chemists, the pressure is constant most of the time. And so that means that this is a really easy thing to say, which is that delta H and Q are the same thing as long as I'm at constant pressure. And again, you don't have to worry about that part of it, because everything that we're doing in class is probably going to be at constant pressure, so it's not going to be a trick scenario. So that being the case, delta H then becomes our heat term. Let me draw a couple of graphs and sort of just refresh your memory about some things that you hopefully know from Chem 1 that will tie us back into this equation here. So hopefully somewhere in the past in your chemistry career, you've seen diagrams that look like this. They're enthalpy diagrams. And essentially what we're showing here is that we have enthalpy on the y-axis here, and then on the x-axis we're talking about the progression of the reaction itself. And so you probably remember that you've got reactants over here, and you've got products over here, and then maybe you've got some sort of transition state here in the middle. Remember that distance is activation energy. Why these diagrams are important is because they're essentially talking about what's going on as far as the enthalpy. Am I getting enthalpy out? In other words, is heat being released, or is heat being absorbed by the system? This is one of these things that sometimes throws science students off, because in chemistry and physics we kind of use different signage for enthalpy in particular. The reason for that is, as chemists, we're worried about the system. Okay, and so what we're going to do is we're going to define these things, and we're going to say that what matters for us here is that in this diagram, I have a lower energy at the end, at the product stage, than I did at the reactant stage, which means that this is what we would call exothermic. And exothermic essentially means that my delta H is negative, that heat is being given off into the surroundings. In other words, the system, the reactions, the stuff that are actually reacting, are giving off their energy to the molecules around them. Okay? Obviously over here in this case, then that would be the opposite case. So our final energy is much higher in the products than it was in the reactants. And so in this case, this is what we would call an endothermic reaction, and our delta H is positive. And what that means is that in this case, the system is absorbing energy, it's gaining energy. The molecules in the surroundings, all the molecules around it, are essentially giving up some energy to that reaction, and so that the final energy of the products is going to be higher than the energy of the reactants. Okay, this is really important to us. And it's important to us numerically because delta H here is part of our delta G, and so the sign here of our enthalpy really matters a lot to us. Okay, so terminology-wise, you need to make sure that you remember that exothermic is negative and endothermic is positive. And the reason I say to remember that is because it's the opposite in physics. And I'll tell you the reason for that, not because there's like some long-standing beef between physicists and chemists or anything like that. It's just that in physics you're not worried about the system, the reaction. You're worried about what can you do to the surroundings. What sort of work can you do to the surroundings? And so the signage works out a little bit differently there. So let's talk a little bit about like a really simple reaction here to talk a little bit about what is going on with our enthalpy and how does enthalpy actually work. So this is a combustion reaction. Combustion reaction is a good example of a reaction that just at the start of, we sort of already know what this is going to turn out to be in terms of enthalpy, because of course the reason that we do combustion is so that we get energy out of the system. And this is obviously methane, this natural gas. We're going to burn it in the presence of oxygen. It's going to give off carbon dioxide and water. Does it do that perfectly? Well, it sort of depends on how much oxygen you have, and we talked about that a little bit earlier in the year. So that's a combustion reaction. Now, what's actually going on in the combustion reaction is that we are breaking and reforming bonds. That's what's true, what's happening in any reaction really, is that we're taking some bonds and we're breaking them, and then we're forming some new bonds on the other side. And so real quick, I want to talk about what kinds of breakages of bonds can we have. So real quick, let me just draw out what a methane looks like. Okay, so that is a CH4, that's our methane. Of course, it's tetrahedral and all that. And if we're going to break this apart, then we can calculate the energy of that. And indeed, we have calculated the energy of those. You can look for standard enthalpies, meaning enthalpies at standard conditions. You can look up a table of those, and you can see what is the value of energy that it takes to break this bond. And remember that it takes energy to break bonds. These things are together now. They're at a low energy state. And to get them to come apart, we have to put energy in to counteract that low energy state. Okay, so it takes energy to break bonds. Breaking bonds is an endothermic process. Okay, so we've got to break that bond there. Now, if we do it in a certain way, and there are multiple ways that we can do it, but if we do it such that, remember that the bond represents two electrons being shared. And so if we essentially send one electron back to each of the original atoms that contain that bond, then that is a specific kind of bond breaking called a homolytic cleavage. Okay, and it's called homolytic because each side gets an electron back. That will form what we call radicals, and that's going to be really important to us later on. We can have heterolytic cleavages as well, and that would be, of course, if we drew our arrows in such a way that they were double-headed, or both sides of the arrowhead there, which would represent that both electrons were leaving. The only reason that I bring that up is because that's going to become important to us if you're taking organic chemistry down the line, or if you're in organic chemistry now, but also because that's where the values on the table come from. And so in the case of this particular reaction here, what this takes is that we've got 435 kilojoules per mole for each one of these bonds that I'm breaking. Okay, and that what that really is 4 times 435 kilojoules per mole, because if I'm breaking down 1 mole of methane, I have to break 4 of those bonds, those CH bonds. Okay, and I should have specifically said that. These are CH bonds in this case. In the case of oxygen, what I would be breaking is double bonded oxygen bonds. Okay, and I have 2 of those, and you're like, 2 because it's double? No, 2 because I have 2 moles of oxygen. Okay, and I've got to break the sigma and the pi bond there, but I've got to break both of those bonds. And so the amount that I get from that is, let me see here, it's 495 kilojoules. Okay, and so that means that just on the reactant side of this equation, I have to put in 4 times 435 and then 2 times 495, add those up together, and I'm going to break that apart. And I'll do the math for you in the other part. It's not super important to us right this second. Okay, so we got to put that energy in and break that apart. On the product side of the equation, then, we are forming bonds. And real quick, let me go back here really quickly and make sure that we label this. Bonds broken. Okay? So we got bonds broken over there. On the other side, we have bonds being formed. Okay? So we've broken this stuff apart. We're going to reform them over here into different scenarios. So it's not oxygen bonded to oxygen anymore. It's going to be oxygen sharing its electrons with hydrogens over here and with a carbon. Okay? And so we've got that going on. So in the case of my water molecule, of course you know your structure of water. Water is this, and I'm not going to draw all the electrons because I'm really just concerned with the bonds right now. So I've got 2 OH bonds. Okay? I have 2, except, so there's 2 on each molecule, but I have 2 moles of it. So that means I have 4 of those. Okay? And so the bond enthalpy for that is 463 kilojoules. By the way, we wouldn't necessarily call that bond enthalpy. Technically what that would be called is bond dissociation energy. It is the enthalpy that's needed to break apart those bonds. Okay, so 463 times 4 over here. So you can already sort of see that my formation here is more energy than my breaking was over here. Okay, for just this part. Now again, there's sort of a split down here between reactants and products. Okay, so that matters a lot. And then we've got one more, or actually two more bonds that matter here. Our carbon dioxide, remember, is a linear molecule. So it looks like that. Okay, and so what that means is that I've got two C double bond O bonds to break there. My energy there is 799 kilojoules, and I've got two of those. Now, I'll pop the math up in the video when I'm editing it for you later, but what you can already see just by looking at this that my formation is higher energy than my breaking is. Okay, so my bonds broken compared to my bonds formed over here. Okay, bonds formed is higher. Now, why does that matter? Well, because to form the bonds, remember that what bonding is you're reaching a lowest energy state, okay? You're going to an energy minimum, if you remember all those graphs back from when we talked about that earlier in the year. So when we form bonds, that's an exothermic process. That means that the sign of all of these is negative. So everything over here is negative. Everything over here is positive. So essentially the way that this process works out is if we were going to do an equation for it. So the way that this process works out is if we're going to do an equation for it, our enthalpy, okay, is going to be the bonds broken minus the bonds formed. Or we could say that it's bonds broken plus the bonds formed, remembering that bonds forming is negative. Either way, actually, we'll work it out. And what you can see here from the magnitude of our numbers is that we're going to get more energy out of this. In other words, this is going to be an exothermic process, which again makes sense. Combustion reaction, it should be exothermic. Why does that matter to us? Because that means if we go back to Gibbs Free Energy up here, okay, so this is our Gibbs Free Energy, that what's going on is that would be a negative sign there. Okay, so that's the enthalpy part of the equation. We're going to come back and talk about the entropy part here in a minute. All right, thanks, kiddos.